No, you just have to understand what's going on.
Oh, thank God.
Okay?
I can't see anything, especially with Ivy's stupid.
Let me fill in this graph here, okay? So, if an isotope contains too many neutrons, all right? So that means there's too many neutrons. We need to create some positive charges. Hello? Mr. Megales. How are you doing, sir?
I thought your name was Mr. Manning.
Okay, you play. Are you doing that right now? No. Okay. So if we have too many neutrons, some of them have to convert to protons. One or more have to convert to protons. So it's going to decay through, we call that negative beta decay. No, that's it. Positive beta decay. So negative beta decay takes a neutron and converts it to a proton.
And releases an electron.
That's right.
That's what we looked at yesterday.
We learned that yesterday. That's right.
So do we have to refer to it as negative, not just beta decay?
Yeah.
Probably. Because there's positive beta decay as well. Yeah. So, too many neutrons means that there's too much compression force in the nucleus, too much strong nuclear force. So it naturally flips a neutron to a proton, but by conservation of charge, it has to release an electron as well. In contrast, if there are not enough neutrons in the isotope, now we're the opposite, too few neutrons, there's two different things that can happen.
Positive beta decay?
Positive beta decay. Which converts a proton to a neutron.
We need that much space?
No, just so you can see better. And yeah, releases a positron. Good work. Well, fantastic.
What is that?
A positron is an anti-electron.
What the?
So if a positron
No, there's not really any
collide
matter.
a lot of
Not a lot, but
isn't a proton an anti-electron because there's not much mass?
No.
that's right.
Because it's
No,
okay then.
it differs in mass.
Oh.
Positron's more similar in mass to an electron than a proton.
Yeah.
That's why it's an anti-electron.
That makes sense.
You get all that stuff just on sale. I'm not thinking.
Okay.
Okay, that makes sense.
Apparently I'm a blender.
Okay, so that's one option. If we have too few neutrons, we flip a proton to a neutron and then release a positive charge because we're losing a positive charge, so we have to release a positive charge. But we're not releasing a proton because we can't make that's too much matter. Nature created this anti-electron, which is very low mass, but still
But does it
a
exist?
positive charge.
Does it exist?
It
in
very
a normal-
quickly finds an electron and they kill each other.
What happens in that type? Like a huge explosion?
No, very small.
Yeah.
If a bunch of them did, it'd be a huge explosion.
Yeah.
Would we notice that it's
No.
No.
Okay, or the isotope, this is a different thing that can happen, can absorb an electron. So if you get an electron that's actually being projected in the near vicinity, a free electron in the near vicinity, it just gets absorbed into the nucleus, like the protons go off and they eat the electron, and then it just cancels out one of the protons and makes a neutron. Okay, so either the protons decay and release a positive charge, or they absorb a negative charge, which cancels out a positive charge. And this is called electron capture.
So this happens because the protons are attracted to the electron.
That's right. The electrons, if it's a free electron that's floating by in the vicinity of the decaying the decaying nucleus, then it can be absorbed into the nucleus, which converts a proton to a neutron.
So the mass of a neutron is the mass of an electron and a proton.
That's right. Yep. So the absorbed electron changes a proton to a neutron. And what do you think it emits?
No, proton to neutron. Nothing.
A negatron.
Just emits a neutrino. That's what a neutrino. It's a massless particle. It's just they're like non-reactive particles, but they are emitted in various radioactive decays.
Why?
We're gonna see in the next couple days that,
why?
that they come into play
What
quite a
is
bit.
it?
Well,
Conserving. Like it's not conserving charge because the charge would be remaining. Like,
what is it? It's conserving energy.
oh.
It's required to
How can it be massless?
Yeah.
because it only exists like photons are massless. They only have mass because they remember we talked about they travel at the speed of light. So if you were to slow it down, it would disappear. If you were to stop it, it would disappear. It only has relativistic mass. So it has mass due to its energy, but then when you stop it, it disappears because now it has no energy,
And-
so it has no mass.
So you know in the data booklet, they only give one equation. Well, we don't even need to memorize that.
Yeah.
What is all this?
What's all what?
This whole page of
Oh yeah,
equations.
we're not there yet.
But do we have to memorize that?
Keep your pants on. Slow down.
So, oh yeah.
Okay. Larger. So, in this same situation, okay, where we have too few neutrons, when we get so this is for smaller atoms do the positron decay or electron capture, but the bigger ones emit the alpha particles. Will produce alpha particles. All right. Talk about that. So again, this EC here is, what do you think that stands for?
Positron.
No, that's E plus.
Where's that's right
What's the
beside it.
EC beside it? Yeah. So the blue in this section, in this area of the graph, represent either electron capture or positron decay. Down here we've got the beta minus decay, or the negative beta decay. And then up here, still with too few neutrons, we've got the alpha decay. And the other ones you don't need to know. Okay, those are very, very rare. They're like super force when for a proton to be ejected from a nucleus, it's highly unlikely.
So we don't need
It's
to know.
only in the extreme man-made cases. Yeah, you don't need to know those. Just the first four there. Wait, what's the fifth one?
Photon.
Gamma. Yeah, and they don't show it. Thank you. Thanks. Okay.
But we learned about the neutron one yesterday.
What's that?
We learned the neutron one yesterday.
Neutron emission. Yes, but that's not a type of decay. That's just a
Type of radiation.
That's a type of radiation.
I'm guessing these
Okay.
decay are just exponential.
Yeah.
We're gonna get there. Yeah. For that's right.
Yeah.
Oh, I love those ones.
Yeah, but we have to memorize them.
You don't need to memorize exponential.
Oh, I hate memorizing equations.
It's not as bad as last year.
Yeah,
In
that was
regards to-
terrible.
I didn't even memorize one equation last year.
Yeah.
It was all in the data.
None of it was in the data.
All of it was in there, but
All right. So now we're gonna summarize the 5 different types of decay, and we're gonna go through examples of each one, specific examples.
So,
Okay.
you have to write the alpha particles feeling like
looks good.
As many times as it takes.
this. It feels like the 7th time we've done it.
What's the symbol? Oh my God, I'm blanking out. What's the symbol for atomic mass?
And Z, A.
Is it A? Right? It's A. Okay. Thank you.
What goes? Oh, that's a Z, not a 2.
That's Z. Yeah. So general equation, we've got element X, whatever it is, Z protons and a total mass of A. Breaks down into element Y. Sorry, my screen's glitching. I have to recalibrate.
Is there an element X? Xenon.
Good job, Zach.
Alright.
I totally forgot about our design lab.
But there's an actual element Y. You can't use Y.
It's just in general. Okay. So, breaks down to element Y. Now, if it releases an alpha particle, what's the relationship between the number of protons on this side of the equation? Yes, Z minus 2. That's on the ball today. Love it. And A minus 4. Fantastic. Okay, plus our alpha particle. Which is
This
just
isn't really an equation, it's just like a rule or a law.
Yeah, you're right.
Oh, that makes sense. No.
Okay,
I
so I'm
thought it
going
would be
to
like a change.
look up specific equation right from your textbook.
Like an example.
No, a specific equation of the for alpha decay. Radioactivity. I'm just doing for like yeah, uranium 92-238.
Oh, it's more like an example.
Yeah, that's why it says specific example. Decays into thorium, which is 90 and 234.
Don't worry. Named after
Plus the alpha particle, 24.
So it's always going to be an alpha particle 2-4?
Yeah,
Because
But are there
helium?
different variations of decay for uranium?
there are, but this is just a specific example where it decays through. It's natural alpha particle decay.
This isn't even.
This isn't the forced nuclear fission type of decay. Okay, this is in the natural world. Uranium-238 decays.
So naturally, without any like man-made.
That's right. Yep. Okay, next one. Beta minus decay, or negative beta decay. It's really easy to remember which one's which because beta minus decay releases an electron. Okay.
Whoa. 0, 0.
Well, but technically there is a mass though, right?
Say what?
There's
No.
a mass.
Isn't there a mass?
Negligible?
No, but in terms, it's very small. So in terms of atomic notation, you just write it as 0.
It's negligible.
Until tomorrow. Then we're doing nuclear reactions, which require E equals mc squared. You need to calculate.
Oh my god, every
Okay, general equation.
Equals of squared of holes.
Oh yeah.
So, an electron is emitted when a proton changes to, no, a neutron changes to a proton. Okay? So if a neutron changes to a proton, which one of those numbers is changing?
Z plus 1.
Z plus 1. Fantastic. Okay, so the atomic number increases by 1, but the atomic mass stays the same.
And then plus E.
Sorry.
It's both of beta decay.
Oh shoot, they also want. Okay. If we're being thorough, it also releases an anti-neutrino.
So how do we do that notation for that?
I'll show you.
It's like an arm.
Seagull with a line over it.
This is just a technicality. I mean, you should probably remember it. The fact that neutrino is released during beta decay. But
Should we write that down?
this is, let's label this, okay? So this is an not anti, anti-electron neutrino.
Isn't it positron?
No, it's
Why?
anti-electron neutrino.
Anti-electron.
Then why did we write positron?
That's different. That's a different decay. Okay, different decay.
Oh right.
All right, specific example of beta decay. Thorium, which we just saw in the previous one, will decay to palladium. So thorium, which is 9234,
90. 92.
90 and 234, decays to palladium, which is 91, 234 as well. Plus our electron, plus our anti-electron neutrino. Again, this last part is just a byproduct of the reaction. It doesn't do anything to the atomic mass. It's just there.
Combined with the neutrino to
Conserve the energy.
That's right. To conserve momentum in terms of the decay. Now, when you get into particle physics, if you take physics in university, you might get in. Depending on how far you get into it, you will. There's a whole bunch of different neutrinos, and they all have different purposes in terms of reactions, tiny little reactions in subatomic particles. But for now, they're just there. Okay, they're a pain in the butt, but they're just there.